Same two equations that we use for exponential decay have parallels for exponential growth. So the first one we'll look at is just like the exponential growth for the exponential decay equation when we're given a rate or asked for a rate of decay, we'll use when we're given or asked for a rate of growth as well. In this problem, in 1910, the population of a city was 120,000, so we'll call that our A, our initial amount. Since then, the population has increased by exactly 1.5%, so R is 0.015. And if the population continues to grow at this rate, which means it keeps following the same model, what will the population be? We're looking for a Y value in the year 2013. Now, we certainly could use the year, the T is equal to 2013, but trying to put a 2013 up there, I mean, that's a ridiculous number for an exponent. So sometimes what makes the calculator's job a little bit easier and leads to fewer problems with their little algorithms is if we use the year equals 0 to stand for something a little bit more reasonable. So we could make 1910 be the year 0, or to make our numbers look nice and prettier, we can use the year 1900 to be the year 0, which would mean T equals 113 to be the year 2013. And so all that they're asking us for is to find the Y value when the T value is 2013, starting with 120,000, multiplying it by 1 plus 0.015, and of course we'll turn that into 1.015 in a second, raised to the 113th power. That's all it's asking you for here. So this question ends up being on the easier side. The trick is just to make sure you are able to decode what it's asking you for and separate that from what it's telling you. 120,000 times 1.015 raised to the 113th power is 645,422. And so if we take a look at our chart, you can pause and fill this in. We've now filled in the third of our 4 squares. We have another model for exponential growth. And I want you to just notice it's really the same as the exponential decay. The only difference here is that the rate is growth, so it's positive, whereas for decay, it's negative. Other than that, it's the same idea. Well, we're going to see the same thing for our exponential growth model using E. It's going to be, instead of having a negative exponent, we'll have a positive exponent. So here's an example that uses that. As of 2000, China was the world's most populous country with a population of 1.26 billion people. The second most populous country was India with 1.01 billion. Populations of India and China can each be modeled. I of t is 1.01 times e to the 0.015 t, and c of t is equal to 1.26 e to the 0.009 t, respectively. According to these models, when will India's population be more than China's? This is one that we're going to handle just on the calculator. Now, the truth is we could solve this one by hand. It's not impossible. But I just want to show you how a good way to do it on the calculator. And one quick thing I want to point out is we have these two numbers here that look an awful lot like percentages, 0.015 and 0.009. It's important to point out that they're not exactly percentages. That does not mean that India is growing at an annual rate of 1.5%. It's actually going to be a little bit bigger than that. Just like with our investigation into bank accounts a couple of classes ago, we saw that when we use the E when we're talking about continuous interest, when you compound continuously, in which case the interest rate is actually an underestimate for the actual interest accrued, right? We saw that if you have a 100% interest rate on a $1 account compounded continuously, you actually ended up with $2.72. So the actual rate of growth is a little bit more than 1.5%. So I don't want you to get confused about that. Either way, when we solve this one by graphing, our strategy is going to be just to graph the two equations. I of t, and it's not a bad idea to give it a name here. You can use any sort of name you want in Desmos. Very few letters will give Desmos will have a problem with. 0.015 to the t, and c of t is equal to 1.26 e to the 0.009 t. So just to really quickly look back at what we're doing over here, the important thing here is when will the population, India's population, be more than China's? What we're really asking is when will it catch up? So when will India's population catch up to and equal China's population? So what we're doing is solving this equation. And it is doable by hand. It's not particularly tricky. It's not something we haven't learned enough to figure out. But I want to focus on the calculator version right now. So what we're going to do with the calculator version is, well, it doesn't really look all that interesting here. We just got a couple of lines close together. But what we can do is fix our window a little bit. You know, we're not talking about populations that are getting into the 15 billions anytime soon, so I can spread this out a bit. And apparently it's going to take more than 10 years for India to catch up to China, so I can drag this in. And I'm just going to do is just drag it in until we can see where they meet. And all we need to do to solve an equation on Desmos is graph each side separately and look for the intersection where they cross. So they'll cross when t is 36.86, or according to the model we were using, since we had t was the year 2000, that we're expecting India to catch up to China in approximately the year 2036. Quick point is that notice how even though it ends with a 0.86, we don't round up because years don't work that way. The year 36.86 will be somewhere in the end of 2036, but we don't round that to 2037. We still say that it is during the year 2036. So what you can do now is just fill in that last box in our chart, and y equals ae to the kt. And again, we're going to choose to use e anytime they don't talk about the r. If they're not talking about the rate of growth or decay, we'll use e. Truth is, we could use either one and we'd get the same answers for most questions. We will also use ae to the kt or something similar to it when we're talking about continuously compounding interest in an investment or a bank account. That's the only exception where we see a percent interest and we use it in ae to the rt.